Ever wonder how scientists actually track evolution? I mean, we can't exactly hop into a time machine and watch genetic shifts unfold over hundreds of generations, right? But what if I told you there's a mathematical way to literally freeze time? Welcome to This Explainer. Today, we're going to unpack one of the most elegant concepts in all of biology, the Hardy-Weinberg equilibrium. It's essentially nature's genetic pause button. It gives scientists a baseline to measure exactly how and how fast a population is evolving. It is fascinating, it's highly logical, and we are going to break it all down right now. Okay, let's dive right in. Here's the roadmap for our genetic detective story today. We'll start with the Hardy-Weinberg principle itself, then open up the genetic math toolkit, use it to spot hidden carriers, and finally run a real-world gerbil population test.
Starting off with part 1, the Hardy-Weinberg principle. Where did this foundational rule actually come from?
To really appreciate the science here, you have to appreciate this absolute historical coincidence. Picture this. It's 1908. Godfrey Harold Hardy, who is a brilliant British mathematician, and Wilhelm Weinberg, a German physician, are working in completely different fields in different countries. Yet, they independently discover the exact same biological law. Seriously, a mathematician looking at numbers and a physician looking at inheritance arrived at the exact same conclusion about how genetic frequencies behave over time. And here is that very conclusion. The Hardy-Weinberg equilibrium states that in a large, randomly mating population, gene and genotype frequencies remain constant generation after generation as long as there is no selection, mutation, or migration. Basically, it's a hypothetical state where a population just stops evolving, a literal genetic pause button. You see, evolution is defined as a change in allele frequencies over time, so the Hardy-Weinberg equilibrium defines a population where those frequencies do not change. If the frequencies are stable, evolution just isn't happening. But here's the catch. Hitting that pause button is remarkably difficult. This equilibrium is incredibly fragile. For a population to stay mathematically frozen, it requires some strictly enforced conditions. First, the population has to be large, and mating must be completely random. Second, there can be absolutely no natural selection. Third, no new mutations can enter the gene pool. Fourth, no migration. Nobody moving in, nobody moving out. And finally, there can't be any selective elimination of recessive homozygotes. If even one of these rules is broken, the equilibrium is completely shattered, the frequencies shift, and boom, you've got evolution.
Let's move to part 2 and see how this builds. We're going to open up the genetic math toolkit.
It all starts with this beautifully simple baseline equation. P plus Q equals 1. In genetic terms, P represents the frequency of the dominant allele in a population, and Q is the frequency of the recessive allele. Since those are literally the only two options for a specific gene in this simple model, their combined frequencies have to equal 100%, or 1. It's elegant, but we run into a practical problem in the wild. We can't easily see who is carrying a hidden recessive gene. And that's because of complete dominance. You just can't distinguish a dominant homozygote, someone with two dominant genes, from a heterozygote who has one dominant and one recessive gene. Physically, they look exactly identical. So we have to work backward. Step 1. We start by counting the individuals who show the recessive physical trait, because we know for a fact they have to have two recessive genes. Mathematically, this frequency is known as Q squared. Step 2. We simply take the square root of that number, which gets us Q, the frequency of the recessive allele itself. And finally, step 3, we plug Q back into our simple equation to find P. We just subtract Q from 1. All right, on to part 3, spotting hidden carriers. This is where things get really fun. This right here is one of the most powerful applications of the Hardy-Weinberg Law. How do we find the frequency of individuals in a population who look perfectly normal but are secretly carrying a hidden recessive abnormality? They are heterozygotes, carrying one dominant and one recessive gene. We can't see that recessive gene with our eyes, but we can absolutely calculate it. Let me throw a crazy number at you, 32%. Keep your eyes on that number, because it's the answer to a very specific, eye-opening textbook scenario. It shows just how many secrets a population can hide. Let's see exactly where that 32% comes from. Imagine we observe a population, and we find that 4% of individuals visibly show a recessive abnormality. So our Q squared is 0.04. Following our toolkit, we take the square root of 0.04, which gives us a Q of 0.2. Now, to find those hidden carriers, the heterozygotes, the Hardy-Weinberg formula is 2pq. We know Q is 0.2. We know P has to be 0.8 because 1 minus 0.2 is 0.8. So we multiply 2 times 0.2 times 0.8, and we get 0.32. Think about that for a second. If just 4% of a population physically shows a recessive trait, a massive 32% of the population are walking around as secret carriers of that exact same gene. No way, right? And this brilliantly illustrates the theory. But let's move to part 4, the gerbil population test, to see this in practice. Consider this a snapshot straight out of a genetic detective's case file. What we have here are the raw notes applying the Hardy-Weinbergh equilibrium to an actual, real-world population of animals. We're going to extract the data from these notes and run a quick analysis. Let's see if this specific population is in equilibrium, or if it's evolving. Okay, let's lay out the concrete facts of our gerbil case file. We're looking at a randomly mating population of exactly 1,000 gerbils. When we observe them and sort out their genotypes, we find 500 homozygote brown gerbils, that's capital B, capital B. We have 400 heterozygote brown gerbils, capital B, lowercase b. And we have 100 homozygote black gerbils, 2 lowercase b's. The notes also establish that the black allele is recessive to the wild-type brown. Now, because we miraculously know all the genotypes in this specific gerbil scenario, we can calculate the exact gene frequencies straight away. To find P, which is the dominant brown allele, we take the 500 gerbils that only have brown alleles, and we add half of the 400 heterozygote gerbils, since only half their genes are dominant brown. That's 500 plus 200, which gives us 700. Divide that by our total population of 1,000, and our P is 0.7. Using our simple baseline equation, Q is just 1 minus 0.7, giving us a recessive black allele frequency of 0.3. Now, what's really interesting here is how we prove they're obeying the pause button. We use what's called a chi-square test. This directly compares what nature actually produced, our observed numbers, against what Hardy-Weinberg mathematically predicts, our expected numbers. Because our P and Q frequencies are so incredibly stable, the expected numbers of brown and black gerbils almost perfectly match what we actually observed. Those tiny, tiny differences give us incredibly low chi-square variance numbers. And that tight agreement, that tells our genetic detective that this population is remarkably stable and is, for sure, in Hardy-Weinbergh equilibrium. Which brings us to a really fascinating final thought. We just proved our gerbils were in equilibrium, but remember those strict rules from earlier? No selection, no migration, perfectly random mating, 0 mutation. Well, out in the wild, outside of controlled tests, those conditions almost never hold up for long. So you have to ask yourself, is any natural population truly in a permanent Hardy-Weinbergh equilibrium, or is this principle actually the ultimate measuring stick?